Hello guys, approximate analysis of structures due to vertical load, frames in this case. We have this frame. As we discussed in the introductory part, we don't, if we have to do this by hand, let's say, it's gonna take forever. So we recur to this approximate method to solve it, and the idea is transforming this into something like that. This is 0.1 L and this is 0.1 L for every one of the inflection points, as I explained before. So basically we're gonna get this thing and convert it into this part here, and we have to start by we don't have to, I like to start by marking these points where those points correspond to the 0.1 L, and 0.1 times 8 is 0.8, so this distance is gonna be 0.8, and the distance at the center is going to be, if this is 0.1, 0.1 is going to be 0.8 times 8 is 6.4. Same thing here, 0.8. And in this other span, this is 12, because this is 12 and this is 0.1 L. Remember, 0.1 L. And because this is 0.1 L, then this is going to be 1.2. 0.1 times 12, 1.2. And same thing here is going to be 1.2. That's going to be in meters, and the distance here to the center is going to be 9.6, which is 0.8 times 12. Once we have that, we can solve this problem by starting the middle part, this portion here. So that portion over there, I'm going to say that is this. And you have the load on top of that. Where are my markers? Nobody moves. Let me get another one because I don't wanna. Another one. So this is the load on top of that, and I can calculate these reactions here if I want to. If I don't want to, I don't calculate it, but I really need to do it. So this is 10 kilonewton per meter. Who is emailing me? Okay, I will talk to you later. And I'm going to have this reaction and this reaction. This reaction is going to be W times L, and this distance from here to here is 6.4. And in this other end, if I do the same thing, I'm gonna have the same issue, same thing. Sorry, here and here. And the load is gonna be here, load of 10, and this distance is 9.6. That will be this part corresponding to the simple support span. So what are the value for these reactions? The value for these reactions is going to be 10 times 6.4 divided by 2, 32. That's the value for this, 32 and 32 kilonewton. What is the value for the reactions here? 10 times 9.6 divided by 2, 48 and 48 kilonewton. That's it. With this I can do everything else. Now the other part, which is the lever cantilever, the little cantilever, it will be here. Let me put it here. The little cantilever will be here. From this part, it's gonna be just this with the load like that. This distance is gonna be 0.8. Same in the other side because it's symmetric. And for this one, it's gonna be something similar. You're gonna have the cantilever here, and this distance is going to be 1.2. Now the reaction that is acting here is going to be reverted to the cantilever, and the reaction that is working here is going to be reverted to the other cantilever here. What do we have? Now if I want to calculate the moment here, we can calculate those moments, and we should be able to also calculate the reactions. What reaction? This reaction here, this reaction, and this reaction. So if I want to calculate the moment, the reaction first, let's say summation, and I don't know how to call this. I'm working here, so this is GY and this is mg. which is going to be the same as this other end for symmetry. And in this case, the same thing. This is going to be HY and MH, and you know what I mean by that. Now, this is the value for the reaction. Once again, this is 32 and this is 48. Now, if I want to do summation of forces in y equals 0, then you have that gy is going to be equal to this value, 10 times 0.8 plus 32, and that's 40 kilonewton. And if I want to calculate hy here, it's going to be the same thing. It's going to be, hy is going to be 1.2 times 10, distributed load, 10, omega equals 10, plus 48, and that's 60. Okay, good. Now I have the reactions. Moment. If I want to calculate that moment, remember this is a distributed force, produce a rectangular force. This distance will be 0.4. This is the same thing. This force here produces this 0.6 is the distance. So if we have to calculate the moment at G at this point, it's going to be 32 times 0.8 plus, I'm already passing to the other side. This is going to be the value of the force. What is the value of the force? The value of the force is 10 times 0.8, so 8 times the distance, 0.4. So the moment at G is going to be this type of moment, and that type of moment is going to be a negative moment, even though I put it like that. When we plot it, we will see. This is the direction for the moment outside. Moment, 32 times 0.8. Actually, this is the same thing. It should be 64. 10 times point. What did I do here? 32 times 0.8. Yes, 32 times 0.8 plus 8 times 0.4. That's 28.8 kilonewton meter. And for the next one, moment at G, that side will be 48 times 1.2, 48 times 1.2, and this load here is 12 times half of the distance, 0.6. So mg is going to be equal to 48 times 1.2 plus 64.8. Now, kilonewton meter. With those things, now we can build the diagrams. How do we build the diagrams? Okay, let's start with the diagram for shear in this part, shear in GH, shear diagram. GH, I'm gonna put here GH. GH, remember what we have in reality is the continuous thing, like that, but we are calculating this. Here is our structure, simple supported. Here is our cantilever. So this is what we are doing for GH. GH. Here, here. Now, let's start with the shear diagram. I'm gonna do shear a moment, okay? In the same thing. Shear. Now, if we want to do shear, this is what we have. I have a force here of shear, which is 40 kilonewton. 40 kilonewton. Remember this reaction? 40 kilonewton, right there. 40 kilonewton. And then, if I'm going only to the edge of the cantilever, the edge on the cantilever, this is 10, the value of the distributed load, and this is 0.8. So that means that this is gonna come, and it's gonna come lower, lowering up to that point, and that's going to be 40 minus 10 kilonewton meter times the distance is 0.8, so it's going to be 32. It's going to come down to 32 right there. And what happened at 32 is that I find this force on the cantilever, the edge of the cantilever, that makes this close to 0. And that will be the shear portion for the cantilever part. Now what happened with at the same point, then we have this simple supported beam. That simple supported beam is going to have a force of 32, which means that at the same point it's going to go up again to 32, and it's going to come down. 10 times 64 is negative 64, positive 32 is going to come up to this end to negative 32, like that, negative 32. And then at this moment, at this point exactly, I'm going to have this reaction that is going to push it up to 0, 32. But then I'm going to find the same thing that I have here in the other end. So at the other end of this, I'm going to have something like this, 32, and the load here, and this thing here. Meaning, what I'm finding here now is this load that is going to take this point and put it back wherever it was, here. And then, this point is going to be, this goes to 0, and now I find this force that is going to make it go back to whatever it was. And then I have this total load here, which is going to be 10 times 0.8, and it's going to go to 40, negative 40 at this point. And at the end of the support, I'm going to have the reaction, which is going to be same reaction as in this end, because everything is symmetric, and it's going to go back to 0. And that will be the shear for this beam. It's the same thing that we have been doing in statics forever and ever. Now you come here and you do the moment, same thing. When you start doing the moment, you find this moment here. The value of the moment is 28. However, it's negative moment. It's a negative moment. So if this is a negative moment acting here at the support, then you're going to go down to negative 28. It's going to jump down to negative 28.8 right there. And this is a positive area. We can calculate it up to here and then calculate this part. But hey, you know what is going to happen, right? So we're going to be doing the same thing. Now let's do this point just for the sake of showing what is happening. At that point is the point that we assumed the inflection point was, and we determined that, and we converted this with the inflection points. So this is 0.8. Well, if I want to find the moment at that point, should be 0. Let's see if that is 0. So I have negative 20.8 plus the area of this shape. The area of this shape, I'm going to put it here, negative 28.8 plus 40 plus 32 times 0.8 divided by 2, because it's a trapezoid. So 40 plus 32, times 0.4, that's positive 28.8 plus this is 0, so it's going to cut this into 0 right there. Now we can keep going to this point, and now what do we have here? The distance between this and this is 6.4, meaning the distance between this and this is 3.2. 3.2 times 32 divided by 2 is going to be the area of that. 3.2 times 32 divided by 2. Then we have 51.2. 51.2. And that repeats to the other end. Exactly the same behavior is going to happen here. So you're going to have something like this and like that. And then at this edge, you're going to have this moment, which is going to be like this. And that moment that is like that is going to be, and it's going to push it to 0. And that will be the shear moment diagram for that girder GH. If you want to do the other girder, which is this girder, well, it's going to be awfully similar. You're going to have, I'm going to start from here, you're going to have this, you're going to have this, you're going to have that. And like that. Loads, 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 loads. That's gonna come really nice in the closed caption, the series of loads that I say, because I say low, low, low. I didn't say loads. 1.2, that's the distance. 9.6, remember this is this, remember this is that. So what is happening to us, basically, when I saw this cantilever for that one, we already did it, we found this reaction and that reaction. Those were 60 and 60, and we got a moment of 64.8, 64.8, 64.8, and 64.8. That's basically what we got there. Let's do the shear moment diagram for the other girder. Shear diagram for this. Come here, find 60, go to 60, up, 60. Now at this point you have 60, this is a negative load, pushing it down. And what is the value of the load? This is 10, and this distance is 1.2. So it's going to be 10 times 1.2 is 12. It's going to bring this to 48. But at the end of 48, we're going to have this force coming from the cantilever, from the single supported portion that we are assuming, and it's going to push it to 0. Now we go back to the single supported portion, and this is going to be pushed back to 48 at the same time, and then you're going to have this other portion, which is this one. 9.6 times 10 is 96. 48 minus 9. This is supposed to be a straight line. Do what I say, don't do what I do. And then you're going to find this a reaction. This is negative 48. That reaction, negative 48, is going to be the reaction coming from the, remember we are in the other side now, so it's going to be the opposite of this one. And then we're going to come back here again because of the reaction in the cantilever, and then we're going to add this portion, and this portion here is 1.2 times 10 is 12, and then you're going to end up to 60, negative 60, and then you have this force which is going to push back to 0. And I'm forgetting, by the way, the yes. Remember, this is a straight line. Now if we have to do the moment for this, same situation is going to happen. I'm going to find this moment. This moment is going to be a negative moment, which is going to push it down to 64.8. 64.8. When you calculate the value here, it's going to be 60 plus 48 multiplied by 1.2 divided by 2. That's going to be positive. This is going to be negative. Positive 64.8, negative 64.8 is going to come to 0. This is the same curve up to this point. What is the value for this? The value for this is going to be 9.6 L squared, 10 times 9.6 squared divided by 2 by 8, or it's going to be 48 times 48 times half of the distance, which is 4.8 divided by 2, and that's 115.2. Positive, negative. This area here is going to be again 115.2, so it's going to close it in 0. And this area here is a negative area also, which is going to bring it down to negative 64.8. And then we have this value, which pushes it back to 0, and then you say yes. And that's it. And that's done. Look how easy it is going from this animal, this beast, and finding the shear moment diagram, and this for the girders. If I want to analyze the column, then I can analyze the column, because you can go to this column here at the center, to the joint H, and you can see that in the joint H I have this moment of 28.8. I have that moment of 28.8 here, and I have this moment of 64.8 in different directions. That means that the column itself has to be absorbing part of these moments here, because the summation has to be 0. if this is 64.8 and this is 28.8, the difference 64.8, 64.8 minus 28.8, the difference is 24. That moment of 24 is going to be the moment that is going to be absorbed by the column at the joint. So you can do that moment of the column at the joint. Similarly, you're going to have the two reactions. You're going to have a reaction here of 40 kilonewton from this end, and a reaction here of 60 kilonewton, meaning these two reactions are transferred down as 100 kilogram to the to this column, which perfectly coincides, by the way, with tributary area if you start applying the principle of tributary area. Now, we only did this part, the top part. What about the bottom part, this other part? What is the difference between this and this? The value of the load. So for the girder DEF, for DE and EF, just multiply by 2, because the load in this case is 10 and in this case is 20, and everything else is the same. Okay guys, I hope this was somehow informative for you, and try to go over it, and try to go over the first part also, which was the basis of why we were doing what we did. And I'll see you next video. Have a good day.